All right, welcome back, Calculus AB students. I'm going to cover the last thing for today, at least, from chapter 4.4, which is the second fundamental theorem of calculus. So we've been looking at these accumulation functions, and one of the ways I can write them, as you know, is f of x is equal to f of a plus the integral from a to x of f prime of t dt. And remember that this t is really kind of a dummy variable because I've got this variable x up here. If I make these two x's, then that kind of changes the meaning. So basically, I've got f of x, which is really my original function, is equal to my known y value plus the integral from a to b of the rate dt. Okay, so what I'm going to do is I'm going to make some changes with the symbols, just because it will look more confusing at first, but it will be less confusing as we go along. So I'm going to call f of x, I'm just going to call that g of x. So I've got g of x is equal to g of a plus the integral from a to x. Instead of f prime of t, I'm just going to call it f of t dt. Now please note that these two equations mean the exact same thing. Instead of f of x, I'm just calling it g of x. So this is f of x, this is g of x. This is f of a, so that's the y value of my known point. G of a is the y value of my known point. Plus the integral from a to x. So the major change here is that instead of calling this f prime of t, I'm going to call this f of t. As we'll see later, so I'm going to write this now, and then we're going to prove it. I can show that g prime of x would be equal to f of x, which makes sense because what's inside here, this f of t, should really be g prime of x. Okay, so how I prove that, I'm going to differentiate both sides, or I'm going to differentiate through by dx. So if I take d dx of g of x is equal to, I didn't mean to erase that much, so the derivative with respect to x of g of x is equal to the derivative with respect to x of g of a, so I'm just differentiating with respect to x across the board, plus d dx of the integral from a to x of f of t dt. And so it's this one that's going to be a little confusing, and that's what we're going to use the second fundamental theorem for. Okay, so let's first do this guy, because I know that. So the derivative of g of x is just going to be g prime of x. And then the derivative of a constant, because that's my known y value, is 0, so that's just going to be 0. And then I've got this term here. So I'm going to rewrite that term, and I'm going to write it a little bit differently. So I've got the derivative with respect to x of parentheses, the integral from 0 to x of f of t dt. Okay, so what I'm first going to do is I'm going to do the integral, and then I'm going to take the derivative with respect to x. So if I do the integral, then I have the antiderivative of f of t, which I'll call capital F. And I evaluate that from from 0 to x, which is f of b minus f of a. Well, b in this case is x minus f of, this should actually be an a, not a 0, f of a. Okay, so now if I take the derivative, I can distribute the derivative, and the derivative of this constant is 0, and the derivative of uppercase f is lowercase f. So that gives me g prime of x is equal to little f of x. And so that's why this just kind of basically proves that this f of t term, which is really f of x, is the derivative g prime of x. But more importantly, it gives us a rule that we can use for other applications. Okay, so what I have here is I have the second fundamental theorem of calculus, and I'm going to first write this as the short form. And the short form says is that if I have the derivative with respect to x, of an integral from a constant a to x of some f of t dt, then this is just going to be equal to f of x. So this is relatively simple. So here I've got the derivative of an integral, and so so when I take the integral, I'm going to get the antiderivative. Then when I take the derivative, I'll get back to this function. The only thing that's changing here is that originally this is in terms of t, and so then when I do integrate it, like I did in the last example, and then differentiate it, then I get it in terms of x. So let's do an example. And this really works well with functions where we don't know what the antiderivative is. So for example, let's say I want to find the derivative with respect to x of the integral from a to x, and I'll put that a down there in a second, of e to the t dt. So I don't know how to integrate e to the t just yet, but I can at least solve this particular problem. Now, this a can be anything. So I mean, it can be 1, it can be 2, it could be 10,000, it could be minus 10,000, it could be pi, it doesn't matter. Notice that the a does not come into play with the second fundamental theorem of calculus. And the reason why is because once you take the once you solve this definite integral and then you take the derivative, you're taking the derivative of a constant, which is just 0. So if we look at this equation up here, what's actually happening is if I got some function of t, like e to the t, and I have the integral from a to x, and then I take the derivative, I just get the function of x. So here, my f of t is e of t. So if I take the derivative of the integral from a to x of e of t, then I should just get f of x, which is e of x. So the answer to this is equal to e to the x. And there's no plus c because this is a definite integral, and when I take the derivative, the constant goes to. Okay, now I want to do the extended or expanded form of the second fundamental theorem. And when I get back and after you do this homework, we'll be doing more with this. Actually, we'll be doing more with a lot of these. Okay, so the expanded form is, let's say I have the derivative of the integral. And instead of going from a to x, I'm going to go from some g of x up to some h of x of f of t dt. And so if I first look at what's inside the brackets, which is the integral, then if I take the antiderivative of little f, I get big F. And so it's going to be equal to big F of b. Well, b in this case is h of x minus big F of a, and in this case, a is g of x. Okay, so far so good. Nothing, no magic. I just took the antiderivative of little f, I get big F, and I put in my bounds a and b. But now the next thing I need to do is take the derivative. So I'm taking the derivative of these things. But because I've got a composite function, I'm going to have to use the chain rule. So I get, once I take the derivative of capital F of h of x is going to be the derivative of capital F, which is little f, of h of x, times the chain, which is h prime of x, minus, and then I do the same treatment on the second one. So that's going to be little f, the derivative of big F, times, little f of g of x, times the derivative of what's inside, which is a chain, which is g prime of x. And so this gives me an expanded rule for the second fundamental theorem of calculus. So let's see how this works. So for example, let's say I want to take the derivative, with respect to x. So I want to find d dx of the integral from, let's do x cubed to sine of x of e to the t dt. Okay, so notice instead of going from an a to just a single x, I'm going from some function of x, which I'll call g of x down here, up to another function of x, which I'll call h of x up here. And so when I carry this all through, this is just going to be equal to f of h of x times h prime of x minus f of g of x times g prime of x. So let's deal with that piece by piece. Okay, so f of x is going to be equal to e of t, but in this case I want f of h of x, and h of x is the sine of x up here, so I'll write that. So this is h of x, and this is g of x down here. So I've got e to the h of x, which is sine of x, times the derivative of h of x, which is going to be cosine of x, minus the function, which is e of t, but I want the function of g of x. So that's e of g of x is x cubed, times the derivative of g of x, which is going to be 3x squared. So if I clean this up a little bit, this is going to be equal to cosine of x times e to the sine of x minus 3x squared e to the x squared. And that is the value of that derivative using the second fundamental theorem of calculus. So with the second fundamental theorem of calculus, either memorize it or at least memorize how to derive it so that you can come up with an answer. But you know you have a second fundamental problem whenever you have the derivative with respect to x of a definite integral with respect to that dummy variable t. And so you can kind of recognize these forms and know that that's where you have to use the second fundamental theorem. And this actually shows up quite a bit later. It showed in Calc 2, and it's kind of hard to see where it's useful right now, but we will get to applications where it is useful. Okay, so that is it for tonight. We've got one more thing to cover in section 4.4, which is the net change theorem, and then we're actually done. And we can move on to logs and exponential functions when I get back. So for now, just keep working on the homework that's due on Friday. All right, have a good one.